Okay, I think we're going to get started. Hello, again, my name is Peter Vachvelushi. I'm a technical sales specialist with Global Test Supply. Thanks for joining our webinar with Gilles via Global Test Supply University. Today's topic is utilizing ultrasound and vibration for bearing health assessment with SDT ultrasound. We kindly ask all attendees to mute their microphones for the duration of the presentation. Please do ask questions. There's a little question box and we will answer them at the end. We encourage you to ask questions for sure. We've been close. I've been working closely as well as Global Test Supply with Gilles and SDT ultrasound for many years. We pride ourselves in being a leader of SDT ultrasound technology. This is a result of our dedication to offering you our products, expertise, service, and competitive pricing. Gilles is going to be the presenter today. He's the district manager for SDT Ultrasound Solutions in Atlantic Canada and Quebec. He has a long background in vibration analysis with iRed Mechanalysis, Intech IRD, Rockwell Automation, GE Bentley, Nevada. Gilles is a level 3 vibration analyst and a level 2 ultrasound specialist. He's taught vibration analysis as well as ultrasound in Canada and the US for the last 25 years. Gilles, we're ready for you. Please take it away.
Hello, everybody. Welcome to my course of mechanical inspection using vibration and ultrasound. This is me without a beard. This is somebody taking a ultrasound reading on an electric motor. And of course, with ultrasound, we're always listening to the data, and this is a Bluetooth headphone. We'll be discussing what I call mechanalysis. SDT interpretation uses ultrasound and vibration analysis to diagnose severity of machinery faults. In this presentation, we'll demonstrate the use of our instrumentation to diagnose severity of mechanical problems. 1. Unbalance using vibration. 2. Looseness using ultrasound and vibration, bearings using ultrasound and vibration, cavitation using ultrasound and vibration, and gear defect using ultrasound vibration. So I use both technologies to do diagnostics. It's better to have two things tell you the same problem is just having one. It gives you confidence in your output. First things first, I like to make sure that everybody's on the same chapter. So I'll just start with the very basics of either vibration or ultrasound. It all starts off with our little time waveform over here. This is time wave is simply a stretched out display of a machine's vibration over time. In other words, it's a plot of vibration or ultrasound output versus time. The time waveform is displayed the result of a complete oscillation, one cycle of vibration generated by one complete revolution of the unbalance. The horizontal axis is in time, seconds per second. So this is one cycle rate. Boom, there's another cycle there, and so forth, so on and so forth. We use this throughout the presentation, time waveform, and the time waveform can be used in vibration and ultrasound. And just to make things clear, we have 3 units of vibration: displacement, velocity, acceleration. Displacement is measured from 0 to 10 hertz or 0 to 600 CPM. It's used for low speed applications like balancing and so on. So it's measured in mils. Then we have velocity, which is a measure of speed in inches per second or millimeters per second. 10 to 2 kilohertz, 600 to 120,000 CPM, used as a severity indicator. Acceleration changes in speed and G's. Anything above 120,000 CPM, so anything that's high frequency, we look with acceleration. Used for high frequency monitoring like bearings, gearbox, etc. And finally, ultrasound, which is dBs and dB microvolts. Ultrasonic energy with a 40 kilohertz center and a 4 kilohertz bandwidth used for high frequency applications like bearings, gear mesh, air links, and lubrication. dBs is for sound in general. Like you'll probably hear dBA for acoustic, for like a trumpet and a guitar, for example, have a different number of dBs. And you can say how well something is within every dB. Like an airplane could be 100 dBs, a trumpet could be 75 dBs, and so on. So the amplitude of sound is measured in dB. Since we're talking about ultrasound, we're always using dB. Microvolt part over here is because we're using electronics. We're using dBA is for acoustics, which is our ears. So just proceed from there. We're going to be using all of these units of measure in this presentation. First thing, we'll talk about ultrasound. Ultrasound measures friction. See 2 things rubbing here. Measures impacting. Measures turbulence. And of course, this is partial discharge for electricity. So ultrasound also does electrical testing, but that's not part of our subject matter today. Today we're just talking about mechanical stuff. So ultrasound is generated by friction, impacts, turbulence, and partial discharge. We're going to concentrate on friction impacts. We're talking about mechanical problems. Most of you have seen this PF potential failure to a functional failure curve. You have the design, installation. Oh, all of a sudden we have the ultrasound right here. Then we have a potential failure. Then the vibration starts picking it up over here. Then you can hear it and heat, mechanical looseness. Then of course it blows up. One more time. First protection level is ultrasound. Ultrasound is your first level of protection. As soon as that goes, you got vibration. As soon as that goes, you can hear it. Then it gets overheated. Then guess what? It blows up. There you go. Nice big picture here. This is how we're going to concentrate on the ultrasound and the vibration. Now, a quick refresher of basic terms of signal analysis. First of all, this is a bearing. This is a sensor with a cable. Basically, what a sensor reads is the same thing as a mass on a spring. When it goes up and down, you put a pen out, it's going to draw a sine wave or a time waveform, right? The frequency is going to one. So basically, we do the frequency, which is the time period from here to here. So I'm applied to the frequency 1 over the time period gives me a frequency. This frequency is over here, and we put a peak depending on the amplitude of the time waveform. Generally speaking, that's how it works. We call that a fast Fourier transform, okay? And that's what 95% of the vibration analysis is using the FFT. This would be a complex time waveform over here, as you can see. As we go through the FFT process, it takes the frequencies out of it and puts them individually on the spectrum over here. Because not everything's a perfect peak over here. Everything is a combination of problems all in one time waveform, which we basically break down to see what frequencies is contained within the time waveform, which tells us what's wrong with the machine. Cool. We're going to start by talking about unbalance, which is the most common source of unwanted vibration. Erosion and dirt are the most usual causes. Simply cleaning a fan may sometimes correct the problem. You can only diagnose unbalance using vibration. You can't use ultrasound to do this. You can only use vibration. Unbalance only occurs at 1 times RPM. The ratio of vibration up to as 1 times RPM should be less than 5 between the horizontal. What I mean there is if I take a horizontal measurement here, a vertical measurement here, if it's unbalanced, I'd have, say, 0.4 and 0.1. So that's a 4-to-1 ratio. Anything that's like 0.5 to 0.1 is over the ratio of imbalance. There you can suspect either mechanical looseness or resonance. But that's another thing. First of all, I just like to point out this is a spectrum we see for imbalance. One big peak at the rotating speed of the machine. And the time waveforms will be all at 1 times as well. Now I want to slightly talk about looseness. Looseness is a condition that responds to other mechanical problems and by itself is not a vibration force. In fact, there are some types of machines that are not even bolted to the foundation, but instead sit on an electronic pack. For example, you have a fan on a roof. For any mechanical guys out there, you know, so you have a fan on a roof, you usually have springs on a fan on a roof, so the vibration doesn't transmit from the fan to the roof to the people inside the building. They're usually on springs. Very similar to electromagnetic pads, that is to insulate the vibration. The tolerance levels for misalignment and imbalance are much higher on that type of setup than you are if something was bolted down. So typically when you have a looseness condition, you'll have a time waveform that resembles this or this. And the moment you see a little peak kind of like this, so on and so forth, and the square wave, it would automatically produce harmonics. Harmonics are multiples of a frequency. It could be a 1 times RPM, it could be a gear mesh, it could be a bearing defect. It's a multiple of a fundamental frequency that we can see on a spectrum. Now you can see from a spectrum, it's a lot easier to see some harmonics and seeing looseness there than on the time waveform. Same thing for here. That's why we use spectral analysis so much to do diagnosis. So this is very common in vibration. These two measurements are done with a 340, and they're both in vibration for vibration analysis. You can also do looseness with ultrasound. Ultrasound can be used to detect looseness. Ultrasound detects friction, impacts, and turbulence. Therefore, when two machine components are loose and impact each other, we can hear it and record it. Here again, we see our harmonics and rotating speed. Boom, 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 boom. And we can see the impacting in the time waveform right here. Okay? So we can detect looseness with ultrasound as well. For example, looseness of a bearing fit on a machine. When you put a bearing, if your fit's not good, it's the shape within the pedestal. If it sticks within it, the housing, it will create a loose condition. If it's very shaky, very little, you can see it with ultrasound. So you can say if you have a fit problem. What's inside of a bearing? So this is what we're talking about bearings. Let's see what's inside of a bearing. What's inside of a bearing? You have a inner race, outer ring, inner ring, ball, and of course the cage which holds everything in the retainer. We call it retainer. It's also a cage. So these are the components we see. BPFI, ball pass frequency inner rings. BPFO, ball pass frequency outer rings. BSF, ball spin frequency, and FDF, the fundamental treatment, which is a case. So all of these components come out in a vibration/ultrasound spectrum time waveform, which we can diagnose it when you have a problem on a bearing. These are defect frequencies. They're not supposed to appear unless you have a problem. There's 4 stages for a bearing failure. First, the friction goes up. If the friction goes up, guess what? The ultrasound goes up. Then the high frequency random impacts occur. Then bearing defect frequencies occur, which we just looked at, BPFI, BPFO, FDF, and BSF. Then once those things appear, all you have is a bunch of looseness because there's no more geometry left within the bearing. Those are the 4 stages of bearing failure. Bearing 4 stage within ultrasound. Ultrasound picks up the early stage of bearing failure, high frequency stuff. Starts to fade off, the bearing defects begin to appear. Ultrasound overrides vibration is so the combination of them. In most modern condition-based programs, predictive maintenance, call it what you want, you use both technologies. Because one doesn't do everything, either one doesn't do everything, but using both, you have all the tools you need to do your condition monitoring. Here's bearing stage 1 and 2. Here's my harmonics of 1 times RPM. Here's my bearing defect frequency zone, there's nothing. Here's my natural frequency, there's nothing. All you says, oh, the friction going up. Oh, ultrasound's going up, so ultrasound's going up. Oh, maybe you should grease the darn thing. So if you don't grease it, it gets a bit worse. As it gets worse, and you have this little skinny scratch on your bearing, it's like if you're pounding on the bearing slowly. When you hit something, like you hit a bell, it resonates, just like when you hit a bell, it rings. So the bearing starts to ring. As it starts ringing, the bearing natural frequency starts growing, and you can see sidebands. That's another term I'm using. And whenever you have those 2 frequencies within a certain span, the same distance from a peak, we call those sideband frequencies, and those are usually 1 times RPM. Anyways, all that means, when I have my bearing natural frequency between 30 and 20, I'm in stage 2. Okay? If something's starting to happen, my ultrasound is growing. Stage 3. On my outer race, my inner race, and my are starting to appear about multiple. My bearings going up, ultrasound. At this point, the defects of all bearings appear as wear progresses. Much more harmonics appear, and the number of lateral bands or side bands increase around the natural frequency of the bearing components. The ultrasound is increasing, wear is now visible, and can extend to the periphery of bearing, especially if the well-defined side bands accompany the frequency. Once you see this type of thing, change the bearing, please. Towards the end, frequencies at 1 hertz are present, but there's no more discerning frequency. The geometry inside the bearing is Kaputski. There's nothing left to have a mathematical relationship. It's just randomly impacting everywhere. So of course you can't do any math on it until BPF5, BPF4 disappear. You can actually hear the bearing at this point. You don't need any fancy instrumentation. You totally missed the boat. It's about to blow up. The whole point is to catch it just when it comes here, so you can change it without any auxiliary damage. And that's the point of vibration analysis and ultrasound analysis in condition monitoring, is to prevent disastrous occasions. You can calculate these frequencies with these approximation formulas. BPFO is number of balls divided by 2 times the RPM divided by 60 times 1 minus the ratio, which is ratio of 8. In other words, if you don't have much information about your bearings, you can still do some approximations to see if those frequencies appear on your spectrum. But there are much more elegant formulas which require much more math. These formulas can be calculated to get precise frequencies for your inner, outer, ball spin, and cage frequency. These means assume the inner race is rotating in the shaft while the outer race is fixed, stationary. All right. These frequencies are also inside most vibration/ultrasound databases, so you don't have to calculate. Nobody wants to go through this every time they have a bearing. So the bearing manufacturers gave us all their bearing defect list, and a database was built. So you don't have to go through all this mathematics stuff. Now let's move to the sensor selection, okay? This is a typical sensor accelerometer which you use in vibration. This is a typical ultrasound sensor which you use in ultrasound. This is an airborne sensor, which is a parabolic disc. This is an airborne sensor, which is a flex sensor, which has a microphone for ultrasound radio. You can both use both these sensors to detect your bearings. Some applications are difficult to reach with a contact sensor, so you use your airborne one. Sometimes airborne is all you need. We move on. Inside our software, UAS3, we simply pick the sensor, boom. Let's put it here. We put the interval of 1 month, the acquisition time frame we want for the ultrasound signal. Then we press this button, and this appears, and we put in the number of the bearing. We select the manufacturer of the bearing. It goes in here and automatically calculates for us the inner race, the outer race, and all that wonderful frequencies. Because see these numbers right here? You take the RPM, you multiply this, but this number gives you an inner race, multiply the RPM with this, and so on and so forth. You can all your frequencies. And you put the rotating speed right here, boom. That gives us, when we look at spectra, it overlays the bearing defect frequency on top of your spectra. If they match, guess what? This one has an inner race defect. Look how fast this thing's going. That's very important here. 37 RPM. I can detect problems at 37 RPM with ultrasound. Over here, the impacting is perfectly proportional also and the time waveform. So I have a certainty that my end tool for SKF bearing has a problem which was detected on ultrasound. So this is new to our software. Just came out recently. We have a perfectly good bearing database, overlays perfectly. We do wonderful things with this. Now I'm going to show you what a structure and airborne sound in ultrasound. Give me 1 moment. You can hear distinctly 2 different types of sounds. The structure-borne sounds more mechanically, and the airborne sounds more bubbly, but nevertheless, you can detect the bearing with either sensor. Now here's another structure-borne with the airborne sensor. Now you can easily hear the impacting, repetitive impacting with the airborne sensor. This with a flex sensor. I've heard on a few occasions where I can just walk around with my stick. Oh, look, I'm hearing in here, and there's a defective bearing just with an airborne sensor. Very practical, very easy. You don't have to have all kinds of people know how to do this. Either it does or it doesn't do it. Now, what's especially for ultrasound is low speed applications. So, for example, if I have a slow speed application, you have to understand vibrations like with Newton's law, where force is equal to mass times acceleration. So, in order to have a lot of force, you have to have a lot of acceleration, right? In other words, the faster something goes, the more force there is, basically. Imagine a rock on a string. As I spin the rock on the string on my wrist, if I don't spin it very fast, there's very low amount of force on my wrist. As the faster I go, the more force there is on my wrist. Anybody experiencing knows exactly what I'm talking about. It's the same for vibration. If you're turning very slowly, there's very little force, therefore the vibration doesn't necessarily pick it up. Whereas ultrasound, We use the natural frequency of our sensor. The RS2T, I don't know if you remember seeing it. It's got this like little tail on it. That gives the sensor a natural frequency of 40 kilohertz. So anything occurring at high frequency will automatically amplify it because our system is a tuned system. So when you have a slow speed bearing, considered to be difficult by many in the vibration world, requires specialty in terms of sensor use and acquisition time. Normally, if you're taking low speed measurements with a vibration system, it can take 2 or 3 minutes to take a measurement. In ultrasound, it'll take us 30 seconds, 25 to 30 seconds. I'll show you right now. This is a hoist. Many minutes of measurement and vibration, only 30 seconds of travel from top start to top. How are you supposed to take this in vibration? You'll have 30 seconds to take it. You can't. So what do? You use ultrasound. What does it give us? It gives us this. I'll make you listen to it right now. You can clearly hear the impacting on the bearing. You can see even the damage on the race right here. So ultrasound is the ideal type of measurement you want. Anything that goes very, very slow. This is at 14 RPM. We picked up the NRAs. Why does it work at 30 to 40 kilohertz? Because, as I mentioned before, using a tune system, our pickup is tuned with our instrumentation. Anything occurring at high frequency, like impacts us up, it will obviously be amplified. That makes our force. That makes our system a much more powerful one to detect amplitudes at very low frequencies. Another example is this conveyor bearing that's running at 238 RPM. See what about the tail? This is the tail right here. That's what gives our sensor the 40 kilohertz natural frequency, and that's what makes our pickup more sensitive than most other ones, because we actually tune our whole system with this little tail part. On this one here is again another picture of a bearing where the outer race, inner race is all calculated for us. We just simply take this and multiply by 238, and it gave us the impact distance over here in the time waveform, and the spectrum right here, bang, 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 bang. We knew it was an outer race problem. So that's how we can determine the problem. If nothing was appearing here, there's no problem. If something's appearing, of course, there's a problem. It's not rocket science once you know how it works. We also have another system called the Vigilant Mobility, along with the 340 machine. The Vigilant Mobility is relatively for us. It takes ultrasound and vibration online monitoring live. Okay, I'll show you how it looks in a few seconds. This is when it's bolted directly to a internal place, so you want to leave it there forever, kind of a deal. You have your 8 channels, which are 8 independent live channels. That's not a multiplex system. It's 8 live continuous channels. Okay, which is power supply goes in. You can also put a tack in here and other type of things like current, draw, whatever you want. You can put some more inputs over here as well. I've written a little balancing program myself, and there's a phase analysis module in here, and I can actually balance this thing as well, which is kind of neat. And so you pick this on, and you have all your pickups going to your sensors, comes back, and you get it's all self-contained. The software is in there. You don't need anything else. Like, you know, most other vibration systems, ultrasounds, you need a software and a computer, then you need permissions from IT. It's a whole rigmarole. Within here, all you got to do is log into the web page. The web page contains the whole vibration software. You can see your FFTs, your time waveforms, your waterfalls, your phase analysis, everything. Your startup, go downs, it's all in one package right here. You can apply both vibration and ultrasound to it as well. This is a mobility package, which is the same instrument here, except it's got its own Wi-Fi transmission and also its own SIM card. So this thing, you can basically have a laptop, say 20 feet away, and connect with via Wi-Fi, or have the Wi-Fi go directly to your network, or if you want to put it there as a temporary thing, it's got a SIM card inside of there, so you can use it's a SIM tower. As long as you have cell signal, you can take your measurements from anywhere in the world, stick this thing on, as long as cell signal, you can watch your software at home and monitor the machine at a great distance. So it's a very useful instrumentation. And finally, the 340, which is our main instrumentation for walk around data collection, it takes ultrasound and vibration. Also takes temperature, and it has a tachometer inside of it. These are the three main things we're going to talk about today. First of all, this is a paper mill, the operator side. These are presses on the paper mill. Presses, okay, have basically a layer on top of it, okay, which erodes with time. So every once in a while, they have to remove the rolls and put ones with new covers on. In this particular instance, when they moved the presses up and down, there was a hydraulic motor which kind of failed. So it dropped down, boom. Oh, schnooks, you screwed up two bearings. So they had to take two old rolls and put it back on until they get those fixed. So we were asked to monitor the old rolls till the new one's fixed, till the next shutdown, because in a paper mill, you don't want to stop. So we put on the vigilance system. This is the drive side of the same presses. You can see the shafts, right? This is the drive side, so that's where it's driven from. On the other side here is a gearbox and a gearbox, so on and so forth. To try to these things go about 150 RPM. They don't go fast. Don't forget low speed stuff. Again, here's the top roll driven side with the vigilance system in ultrasound. You can clearly see the impacting within the time waveform. These little picks sticking out there, okay? And every one of these are measurements. So we can go back in time anytime we want and look at whatever we want all the time. We'll move along. Here is the ultrasound also spectrum we can see with the vigilance system. Here is a vibration demodulation. So if you want to see the ultrasound signal, or if you want to see a vibration, you can do both on this vigilance system. Again, you have a whole history behind it and so on and so forth. There is the velocity for total severity. Look how low this number is for velocity. You don't really see any problems with BPFO yet. So we're just monitoring at this point. Then we have the top wall driven side, the 340 US3, and we have a sound. So I'll play that sound for you right now. You can't take too much with this sound. It's like it sounds like it's just fluttering. But once you look at the spectrum, oh, look at this. The peak clearly stand out, telling you this is an outer race fault. Okay, I know it's an SDF bearing. There's a bearing part number, all wonderful stuff, and the ultrasound system. Again, the same thing. The driven side. Look at how the BPFO is even clearer. I put the bearing cursors on. BPFO gives me what frequencies: B1, B2, B3, B4, B5R, and so on, and the delta F between every one of them. You can see the speed is 150 RPM. So this thing is not going very fast. Again, in the ultrasound signal again, you can see the impacting. Boom, 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 boom. Clearly seen in ultrasound. Of course, I have to zoom in to see it, so on and so forth. Then again, it's 150 RPM. Then with the vigilant, we can ultrasound waveform also. That was in the UAS3. Now it's in the vigilant. Vigilant gives us the same information as our UAS3 software. And of course, here's the vibration, because I can see it's no, this is ultrasound DMR. I'm sorry, this is the ultrasound signal. And of course, the next one's gonna be vibration, DMR. This one, so we can see both in vibration and ultrasound the bearing defect frequencies. So if you don't see it in one, you'll see in the other. No matter what, you'll be able to capture your problem, no problem at all. Then eventually, it gets into velocities. I explained at the very beginning of this presentation. The moment you see something, BPFO and velocity, this is the time to change the bearing. You can tolerate it inside ultrasound, you can tolerate it inside demodulation, but the moment it appears at velocity, it's time to change the bearing. Here's a different little, the next one, okay, the bottom roll driven side with the impacting. I'll make you listen to this one. Very clear, you know, there's impacting the sinus clearly here. That's one thing about ultrasound. It's made to bring the high frequency data through a mathematical process so you can actually hear it. It's designed to do that. Vibration is not designed to do that. Ultrasound is. The whole point of using ultrasound is to bring the high frequency stuff to a low frequency area that your ears can hear it. When you have some kind of headphones for vibration, you hear the whole machine. But this is specific for a certain frequency. It's a filter. Again, here, look at the beautiful spectrum. Again, the bearing defect frequency. Again, now with the overlay with the bearing defect frequency. And then again with the impacting ones. As you can see, you can easily diagnose bearings of any kind at any speed with a combination of ultrasound and vibration. Ideal for wind turbines, ideal for low speed machinery, high speed, it makes no difference. We do it all. Also, here's a trend of vibration and ultrasound. Here we have the overall and vibration. So we can trend both simultaneously at the same time. You see there's some peaks at the same time when machines stop. In ultrasound and vibration, just the levels are different because of two different units of measuring, two different measuring instruments. Again, we get the vibration DMOS showing us the bearing. The ultrasound DMOS showing us the bearing. So I just basically showed you any bearing can be detected with ultrasound and vibration. If you don't see it with one technology, see it with others. So it guarantees you not to miss anything. And that's what you want at the end of the day. What can go wrong on a gearbox that will generate friction, turbulence, or impact? Don't forget the drive of the gearbox, the coupling or belts. So all this stuff has consequences. Gearbox problems. You have worn teeth, misaligned gears, chipped or broken tooth, eccentric gear wheel producing one or a series of high spots, poorly greased bearings, poorly oil-fed bearings, higher gear tooth friction, misaligned pulley or coupling on input or output shafts of the gearbox, cavitating fuel pump, block or control airflow. So all kinds of stuff can happen to your poor gearbox. So you have to be able to monitor it properly so it doesn't fail. Because sometimes getting another gearbox is not easy. Oh, we don't have one. There's a 6-month lead time to get another one. Then you're in deep, deep trouble. Lack of a better word. Where to take the readings? Another good question we have. Well, you need to take account what we call an ultrasound specific acoustic impedance amount. It's basically resistance. Okay, it's a very extensive resistance. Okay, when a sound wave travels in one medium, reaches a boundary with another medium, some portion of the sound waves reflect. In other words, when I go from one type of metal to another type of metal, but the transition, we want to lose sound. It was some reflected. If it was all the same metal, it would travel all the same speed through a metal. But once you have different metals, there's always a rebound effect. So the further you are from your bearing, the less the sound will travel. Therefore, you want to put your pick as close as you can to your rolling element bearing to get the best signal possible. Should be obvious, but there's a reason theoretically, mathematically to do so. The amount of reflection is governed by the specificities of the two materials. For example, rubber, it does not transmit very much, whereas metal does. Need a reading on each bearing housing if possible, and you might need speed info to get a performance analysis. As you saw in every one of my circumstances where I did show you a bearing defect, I need to know the speed. Because take the BPFI times the speed gives me the frequency I'm looking at. That's the defect frequency. That's the way it works. Here's a gearbox. You can see I can't see too much in here. I'll make you look into it. As you can tell, it didn't sound like much, did it? Not at all. But the moment I look at the spectrum, oh, jeez, look at that, ping, 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 ping. And look at the frequencies. Oh, this is like geometrically, which is that number of teeth times RPM, and I got harmonics in my ultrasound signal. Is there a problem? Just open up the gearbox. Look at that. Tooth damage. Detected ultrasound, it did not see too much in vibration. Another reason to use ultrasound and vibration or a combination of both technologies is not to miss anything. Because in the VA department, they'll never acknowledge you when you do the right thing. They only come after you. How come you missed that? How come you didn't see that? Well, guess what? You protect yourself. You take all the technologies possible so you don't miss anything. Trust me, I've been there. Okay, here is a wind turbine gearbox. Okay, you have your shaft over here, which is going about 14 RPM, 15 RPM, very slow. Then you have your planetary gearing over here, and so on and so forth. And you have your speed increaser, because let's face it, a wind turbine's going at 14, and our thing in North America at 60 hertz. So the generator on the other end of this thing's got to turn pretty fast. So this is a gearbox which brings up the speed. Now we want to be able to detect the problems with the bearings or the gears within that planetary gearbox. First, again, this is our vigilance system. We have time away from, we can start seeing impact being. You can see there's nothing else in the impact. It's repeating itself. There's a little impact at 675. That's not making me go crazy. But then I started doing some more studying. The high-speed gear goes like this, and therefore at 675 speed. And all of a sudden, I started zooming into this little area here, and all of a sudden, oh my goodness, I had this on my image. So again, ultrasound shows me the problem. Next thing I'd like to show you that we did gearbox, we can see with ultrasound. We did bearings, we see ultrasound. Let's look at pumps now. We also did looseness. We also did unbalance. Now we're going to do pumps. Pumps, we cover bearings, which we've done. Coupling alignment, which is another thing, because the one thing I did not mention today, we can verify the conditioning of your couplings with ultrasound by simply listening to it. It's not the scope of this presentation today, but it's a very important part of condition monitoring. You also look at our seals, our cavitation, our mechanical looseness, and suction and discharge valves. Valves are very important in pumps because a lot of times they're neglected. Now, cavitation is a big killer of impellers. You can see how damaged these things are. That's not very pretty, is it? You want to detect the early stages long before this stuff happens. Cavity is caused by implosions of vapor bubbles in the liquid. Implosions of impeller remove surface material. As well as here is the bubbles popping. So, what does that sound like? Because after all, this is my ultrasound. It's all about sound. Sorry about that. Okay. This is what you hear for the popping sound of a problem like that. I have a much better video in a couple of seconds to show you. Move along. The other thing that's very important is the valves. Around pumps, there's all kinds of valves. We inspect the pump, we never look at the valves. Minor issues on the valves can have major effects on the pump. Check is also for passing, for non-return valves, making the stem by pump turn backwards. I've actually seen this on a few occasions where I didn't put the valves on and the other pumps were turning the wrong direction. Here I have a little demo I'd like for you to listen. That's basically on cavitation, valves, and pumps and stuff like that. Here it comes.
Metal erosion is a costly problem. It attacks pumps, valves, piping, and other expensive equipment. No matter what type of liquid is being used, there's always the risk of damage from flashing and cavitation. Wherever there's a restriction in flow, the decrease in pressure can cause a fluid to reach its vapor point. Flashing occurs when the fluid vaporizes and remains a vapor. Metal erosion caused by flashing appears smooth and shiny. Cavitation occurs when the fluid vaporizes, then returns to a liquid state as the pressure increases downline. The metal damage caused by cavitation is rough and irregular due to pitting of the surface. Cavitation is a major source of damage in control valves and other components. Cavitation occurs as a liquid passes through a restriction, such as a valve. The restriction causes the liquid's velocity to increase and its pressure to decrease. The point of maximum velocity and minimum pressure is called the vena contracta. Vapor bubbles form in the liquid when the pressure falls to near the level of the liquid's vapor pressure. When the pressure recovers downstream, the vapor bubbles implode and return to liquid form. After the initial bubble formation and collapse, the bubble may reform and collapse a second time. Liquid microjets form when the recovering pressure makes an indentation in a bubble. Then the microjet bursts through the bubble. These implosions can also cause local pressure waves of up to 100,000 pounds per square inch. The combination of pressure waves and microjets can cause severe damage to the valve plug, seat, and body when they're located near the material surface. Cavitation can also cause unacceptable noise and vibration that reduce efficiency or lead to loss of process control. Even though cavitation occurs, it doesn't always cause damage. The extent of cavitation damage is affected by the following factors: the intensity of the cavitation. Greater drops in pressure increase the potential for damage. The materials used in the construction of the area where the cavitation occurs. Hardened materials reduce damage. The length of exposure to cavitation. The more frequently that cavitation occurs in an area, the more likely it is to sustain damage. Valve size. Increasing the valve size tends to make the effects of cavitation worse. The design of the valve and trim in the area of cavitation. High recovery ball and butterfly valves are more susceptible to cavitation damage. If there is leakage occurring when a valve is closed. Fluid leakage moves fluid from a high pressure area to a low pressure area, which results in cavitation and potential damage. Cavitation damage can be reduced by altering or accommodating any of these factors. Cavitation damage can often be reduced or prevented by using the proper components.
As you can see, cavitation has a big problems on valves as well as pumps. By taking a measurement with ultrasound and the input and the output of any valve or pump, you can detect the cavitation, even flashing. So ultrasound is a very useful tool to do this, which you can't really use vibration for. I just want to show you what we can do with it. Okay. Now, let's look at an SL of, again, a wind turbine. We have our main bearing, our gearbox, a generator. We just went through that with the planetary gearbox, because this is our example. This is what we see in decibels and ultrasound with one of our systems. In system overview, we see all this, the bias voltage of all our pickups, the RMS mode, the peak, and all that stuff on everything we see. And we can see where it's high, low, and so on and so forth with the alarms that we set up. Then you can see as expected, you see impact, bang, 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 out here, which of course means we have a problem. And of course, we have this kind of impacting also, which we'll listen to very briefly. That was pretty obvious as a problem on a bang mirror, right? You can hear it again, slow as heck. You can hear it perfectly. And then we said, okay, we need some grease. So we have the 20 dB. We stopped the machine and we used it. We had 10 dB. So that's one thing about ultrasound is for greasing. Then we put the input, the bearing defect frequencies to get the frequency we're looking for. Then, of course, here's the impacting event as well, and the harmonics of the outer race, which was all calculated, all using our wonderful technology of ultrasound. That complements or finishes my presentation. I hope you enjoyed it and learned something from it. If there's any questions, please ask. Thank you very much.
Thank you, Jill. That was a great presentation. On behalf of Global Test Supply University, thank you all for attending. We hope you found the webinar informative and helpful. Global Test Supply is available to assist you in any way. Simply visit us on globaltestsupply.com for anything you need. Through globaltestsupply.com, you'll have access to our entire SDT ultrasound products with description and specifications. You'll also find out where to contact us and reach any of our technical support staff to answer any questions you might have. At the end of the webinar, we have a short survey that we'd like you to complete. Your feedback will assist us in improving and allowing us to bring you more topics that are of interest to you. We have the upcoming webinars for the next few weeks and months. Please visit the schedule on globaltestsupply.com for the full list of webinar topics. Don't forget, there's a thank you for attending. One person will be getting a $100 gift card to globaltestsupply.com. So let's take a look at the questions. I have 2 questions so far. The first question, when is vibration more important for doing machinery analysis than ultrasound?
Vibration and ultrasound both have their place. For example, vibration can detect unbalance, as I said, but ultrasound can't. Ultrasound can detect things that vibration can, for example, for lubrication purposes, and also for couplings, which we did on board today, but it's another very important test method. So they're both needed in a properly configured condition-based monitoring program. They're both important.
Good. The other question is also on vibration. Do we need to take the 3 axle measurements for vibration, or is one axle enough?
Yeah, on certain points of the machine, for example, what's next to the coupling, you take an actual measurement to verify the alignment, but on a non-drive end of both machinery is not very useful. If you like to have too many measurements, do it if you want. But at the end of the day, when you take your horizontal, whatever you prefer measurement, if it's gone up and you trend, you go back and take a bunch of measurements, then you do a full analysis. What I like to take is horizontal, actual, horizontal. It gives me 6 measurements on a machine, which gives me enough data to trend. In the moment I have a problem, I go do a full analysis. If you want to take 3 times 4, 12, 3 times, sorry, you want to take twice as much data to come to the same conclusion, do it. I just prefer to minimize my time by doing the data collecting and take most of my time to do the vibration analysis, which is more important as far as I can.
Perfect. Thanks, Joel. I have one more question that just came in. How do you take ultrasound readings on a hot well pump? I guess, are the sensors?
Well, you can take an ultrasound with the air. You know, there's one that's like a flex. You don't actually have any contact to it and listen to it. Or we also have a needle probe about this long. You can touch it. You won't affect the pickup. So if you take a needle probe, you just stick it on there. Suppose the needle probe is about, say, 11 inches long. You won't get hot either. It won't hurt the sensor, and you'll have an adequate reading to hear if it's a good or bad bear, or if you're cavitating. It does the job.
Perfect, perfect. That's all the questions we had. So Gilles, thank you again. And on behalf of Global Test Supply, thank you for attending.
You're very welcome.